going to give a little overview of why I think doing quantum information in high-dimensional systems is intrinsically interesting and useful. And as announced, it's supposed to be a very informal talk, so please just if you have questions, interrupt me, or I guess you'll have to somehow get to the microphone. But I'm happy to discuss any of the things I mentioned in more depth. But let's get started. So in classical information theory, one of the fundamental realizations is that essentially everything I can express, I can also express at the level of bit strings. And that is a very useful insight, especially since it's very easy to build bit-based technologies in the sense that they interface with each other well. It's kind of the epitome of abstraction, because I need not care anymore what that 0 or 1 has as a physical carrier, so I can essentially forget about the physics for a while and really, I mean, be it in a CD where like basically laser probes a hole, it be HDDs where magnetization of certain regions, or even the old punch cards where there's hole or no hole, or just modulation of electromagnetic waves. All of these are used to encode bits, and in the end, I don't need to care, because for information processing theory and limits, this is universal. And in quantum information, the same is kind of true. Every quantum information I can encode in a sequence of qubits. So in that sense, this is already absolutely universal. And essentially, the only added benefit is that instead of just having bit strings, I can also process superpositions of bit strings, and that leads to entanglement and other phenomena where interference can be cleverly orchestrated in computation, or entanglement can be verified after non-local distribution to prove security of some communication tasks. And technically, quantum, like classically, I could, of course, also choose more symbols. I mean, there is no need for information theory to work only with bits. I could, of course, also encode in higher dimensional symbols and then also translate between the two. So here's a simple translation. I mean, if I have 4 different symbols, I can, of course, encode the equivalent of 2 bits. And the same is true in quantum systems. If I have a Q-quart, as it is called, or a 4-dimensional quantum system, I can encode just as much as 2 qubits. So then, in the end, if in the classical realm, the realization is, well, I could use anything. I could use any size alphabet, but the easiest to work with an interface is bits. So all classical information theory is built on bits. In the quantum realm, this has been basically the start where people thought, okay, let's just translate everything classical to quantum by using qubits instead of bits. But there is a difference. And the main difference is that in the classical realm, these encodings can be easily made very noise resistant because of redundancy, because of the easiness to copy. So I can amplify signals, I can correct for errors, and none of it affects the way I store and work with information. So classical information, the beauty of it is that it can really forget about the physics. However, if I really want to use superpositions and entanglement, usually I have to encode in very fundamental degrees of freedom. I cannot just do some very redundant bulk coding. And there I'm a bit limited by the ability to control and to isolate and to make them interact. So like local gates and non-local gates are not easily the same. And if my signal diminishes, I cannot just copy and amplify it in a trivial manner because of the no-cloning theorem. And that just means that there is a physically significant difference to the classical realm, because once information is decohered or lost, it's not easy to recover. And unfortunately, quantum information forces us to think about the physics again. Okay, but I mentioned entanglement. Let's define it a bit more formally.
So just a quick question. So in the classical world, do we have like examples of Q dates? Or sorry, I mean,
a trit.
instead of bits, like dates of that's being used, because mostly this is 0101. So is
Exactly. So because of the universality of encoding in bits and the easiness of error correction, I think in the classical realm, almost everything is always bits. Of course, there are some applications of even like analog computers that were explored that are really, really high dimensional and will be discretized in a high dimensional alphabet. And to my knowledge, the Soviets in the Cold War also experimented with building computational architecture based on trits, like 012 instead of bits, but it really never caught on. Okay. Because the amount of information storage of a bit was never the limitation.
But I think in the case of quantum, high dimensionality brings in some unique advantages, and that's why we might.
Exactly, that's the whole point. I mean, like, so far, I think the message is that, well, if I'm easily able to correct all errors, and if I can just copy the information arbitrarily, then both qubits or bits are so universal that I don't need to think beyond this. But as we know, this is not the case in the quantum realm, and here we'll see some unique advantages.
Okay.
But before we can see them, I'd like to just briefly formally define entanglement. So, okay, if I write down a quantum state of a bipartite system, I can find any basis whose vectors I denote with I and j, and expand any bipartite state in that basis. And I can then do what is called a Schmidt decomposition, basically bi-orthogonal decomposition. I can always write every pure state as a sum of bi-orthogonal vectors, where these are now called Schmidt decompositions. And the number of these coefficients, the non-zero coefficients, is called the Schmidt rank, or also the dimensionality of entanglement, because it's really it's the dimension, the physical dimension of the system I really need to represent the correlations of the system. And as we all know, pure states are a nice, convenient fiction and idealization to better understand the theory. But if we ever go to the lab, we will not encounter any pure states. In fact, every experiment we do, every state we encounter in the world will be a so-called mixed state. And every mixed state I can represent as a convex combination or probabilistic combination of projectors onto pure states. And now the question is, well, is there entanglement, and how much entanglement is there in such a density matrix? And that is a tough question in general. This is because I formally wrote here decompositions. There are infinitely many of them. This is not unique because there's this convex space, state space, and in the end, there is no one unique way. This is the right decomposition for a density matrix, but on the contrary, there are mostly infinitely many decompositions. And that's a huge problem because if I want to find entanglement, I cannot just speak about one decomposition, but I have to kind of speak about the set of infinitely many decompositions of the density matrix. And that's why there's usually the definition. For instance, I can define the dimensionality of entanglement for mixed states as the minimum over all possible infinitely many decompositions of the highest Schmidt rank among this decomposition. So it's, and this is known, like knowing this fix exactly is a very hard problem. Yeah, but okay, why would we even care about that high dimensional entanglement? So one of the most easily intuitive claims is that of noise advantage. So let's imagine I have an experiment, typical quantum optical setup, and let's say I create some entangled photon pair in a degree of freedom which is intrinsically high dimensional, for instance, momentum or frequency, time bin, whatever. And if the target state were a maximally entangled state, and then I have detectors and I do the usual, I post-select on coincidences and hope that these coincidences are actually stemming from the source, from the target state that I wanted to have. And there's a probability, though, that these coincidences actually come from so-called accidentals. It could be like a dark count in the detector spontaneously happening while the other photon arrives, 2 dark counts, maybe some environmental light that shines upon the detectors, whatever it is. And let's say, for the sake of the argument now, that this noise is wide, i.e. equally distributed. So no matter, like, the noise is the same for each outcome setting. Then what I'll see is a so-called isotropic state. So with probability PA, or the probability of an accidental, I'll have just noise, and with probability 1 minus PA, I actually succeed in creating the maximally entangled state. And then I can just do some simple math and work out at what probability that state becomes separable. And that probability works out to be d over d plus 1, where d is the dimension of the maximally entangled state. That is quite remarkable, because that means the amount of noise I can add, for instance, for a qubit, where the dimension is 2 or 3. So I can add 66% noise, and then the state is going to be separable. But before everything under 66% noise will still feature entanglement. But as I go higher and higher, like in dimension 9, I'll already have 90%. So in the end, I can add more and more noise. And as d grows really, really large, essentially it shows that almost all entangled states along this line are entangled. So I will be able to identify entanglement even when almost all the clicks stem from just random environmental noise. Such special is the distribution of correlations of the entangled states. But of course, so this shows that, technically I just have to code, I don't know, in 10,000 dimensions, and no matter what I do, I will always find entanglement. But of course, it's not as easy, because this model here assumed that the noise is kind of independent of the dimension of the system. And here again comes technology. Like, of course, as we increase the dimension, we also increase the experimental challenges for building devices that can actually distinguish these outcomes with the correct fidelity. So what are the challenges now to actually realize this noise advantage? So first of all, where can we find high-dimensional entanglement? So is there a physical availability even? Second, well, as the Hilbert space grows larger and larger, basically measuring every possible observable no longer becomes an option. So how do we efficiently confirm its presence? Next, like as I've already mentioned, the noise advantage we've just seen is promising, but a bit naive. Like, under which physical conditions will we actually find such noise advantages? And the last, well, okay, let's say we find it, we certify it, and we distribute some really noisy entanglement. Is this still any good? I mean, it could just be that, like, for doing all the quantum protocols, we need super pure states, and the fact that very noisy entangled states exist might not really be helpful. So these are the 4 challenges I would say we have to address, and these are all challenges that the community in the past years have quite successfully addressed to actually realize some proper advantages. But let's go chronologically. So first of all, where do we find it? Well, that's the easiest. Essentially, in the workhorse of quantum photonics, which is parametric down conversion, high-dimensional entanglement exists for a very simple physical symmetry reason, which is the conservation of momentum and energy. Is there a question? No.
No, there's no question. You continue. That's what I'm preparing for, sir.
Okay, perfect. So momentum conservation means that if there is a pump photon that creates a pair of signal and idler photons, that momentum conservation means that the momenta of the 2 created photons will have to add up to 0, or to the momentum of the pump. And the energy of the two will also have to match the energy of the incident photon because of energy conservation. But since the uncertainty principle tells us that neither of these quantities can be infinitely sharp when pumping, it means that we have kind of a coherent superposition of different momenta and of different energies. And so already the tool we standardly use for polarization or for qubit entanglement is already suitable for high-dimensional entanglement. So here I just put the photonics, but we also have some papers now with ion traps. Also there, of course, addressing one energy level is quite natural to make a qubit, but almost all atoms have a couple of energy levels I can pump to. So a certain degree of high dimensionality is actually rather ubiquitous and rather the norm than an exception. So often it's kind of tedious to break systems down to qubits because they're naturally high dimensional. Okay, so that's first challenge overcome. We don't actually need to do anything, it's already there. And then of course, how many measurements do we need? So here, if it all depends on how many outcomes each measurement can distinguish. So this depends a lot on the number of detectors I have or the way I do the measurement. But in principle, if I have d outcome measurements, then I would need d+1 squared global settings. So in a 1,000-dimensional system, I already need 1 million different settings, already bipartite. I mean, might still be doable, but not really optimal. But once I go to even larger numbers, this 2 will be replaced by n, and tomography is quickly becoming quite unreasonable, especially if I want it to be statistically significant and the error bar is low. But I actually don't need it. If I know which state I wanted to create, and this is usually the case, right? I mean, as I said, we have our target states coming out of conservation laws. Most experimentalists don't go to the lab and just say, oh, I'm just going to create a random state. They rather have an idea about the physics and think they know what state they're going to measure. And this already scales much nicer. This is just goes with d+1, so square root. But indeed, if you just want to confirm entanglement, there are very good witnesses that usually only take 2 different measurement settings. So actually measuring in 2 what is called mutually unbiased bases is already enough for confirming presence. So I mentioned mutually unbiased bases. What are those? Neat mathematical tool. There are 2 bases that are both orthonormal. This is this part. And if you look at 2 different bases, the overlap is 1/d for all pairs of vectors. So basically what this means is if I know the outcome in one basis, I know nothing about the outcome in another basis. That's why I call it unbiased. And just a fun fact, there's this maximally entangled state I mentioned before has a cute symmetry, namely that if Alice does a unitary and Bob does the conjugate unitary, the state doesn't change. This is another neat feature of this, because it means that the maximally entangled state looks the same in all mutually unbiased bases, namely perfectly correlated. And now the idea about these 2 measurements that we had once was, okay, how about we just measure the correlations in one basis and measure the correlations in a mutually unbiased basis? So really 2 clique matrices of outcomes, and then see if we can use this to lower bound some measure of entanglement. And this is something we did with Paul Erker, one of my postdocs, and Mario Kren, who now leads a group on machine learning in Germany. And this was more a theory proposal. And we later thought we can generalize this for every pure state, because this was for maximally entangled state and it relied on the symmetry. But for every pure state, we were able to generalize a theorem to prove that every pure state is uniquely determined by these 2 measurements, or by a measurement in Schmidt basis and one tilted basis, i.e. a basis that looks almost unbiased, but has a bit of a different overlap matrix. So I might know something about the outcome in the other basis. And the idea is rather simple again. So if this is true, if every pure state is determined by two measurements, well, maybe we can just do these two measurements according to the state we wanted to create and use these two correlation matrices to lower bound some measures of entanglement. And then I had the great luck to be, well, actually, because we were a theory group, but back then, Mehul Malik came with an interesting proposal. He was a super great experimentalist, and he just finished a postdoc with Anton Zeilinger. And we had worked together on lots of experiments, and so we decided actually to build our own lab. So, and this was the perfect opportunity because we had just proven this theorem, and we thought, okay, can we actually do it? And together with my PhD student Jessica and Natalia, who then became Mehul's PhD student, Nico and Claude, we managed to actually take these two measurements, this experimental data, and use it to prove a lower bound to fidelity with a certain target state, and then in turn use a theorem connecting the fidelity with the entanglement dimensionality or the Schmidt number of the mixed quantum state. So that was the start. And then
just a clarification. So this tilted basis that you were talking this last slide, that is a mutually unbiased basis or it's not? The tilted basis?
The tilted basis, sorry, I didn't go into much detail. The tilted basis looks a little bit like a mutually unbiased basis, but the matrix of overlaps is not 1 over D, but it's basically, it can be a little bit skewed. So you can write down, you can write down a matrix of overlaps, and mutually unbiased would mean all of the overlaps are 1 over D, but the tilted basis is anything where you slowly tilt, and it depends on the target state. So if the target state is maximally entangled, then the tilted basis is the mutually unbiased basis. But if the target state is not fully entangled, then the tilted basis is basically a rotation somewhere between the Schmidt basis and the mutually unbiased basis, but you stop along the way, so you don't fully rotate there.
Well, so in this case, do you know a priori that the state we are investigating is maximally entangled or very likely to be maximally entangled? Is that the...
That's a very good question. So, of course, I will not know. So what we actually do is we measure first in what we believe to be the Schmidt basis. So that is usually the basis which is bi-orthogonal, which is determined by the conservation law we tend to exploit. So if we want to have frequency bin entangled photons, this would be measurements in frequency basis. If we have momentum entangled photons, we're going to measure in orbital angular momentum. And then we'll basically guess the target state given from the diagonal elements of the matrix. So for instance, if they are equidistributed, we guess it's the maximally entangled state or something else. And then we just construct the tilted basis from the measurement in the first basis.
Okay.
And the nice thing here is that I don't need to assume anything about the state. And if my guess is wrong, it doesn't make the method false in any way. It's just a way of trying to determine the optimal measurement basis to be subsequently used. So if I make a mistake, I will just not find any entanglement, but I will never wrongly find any entanglement. So that's the whole game of certification here.
I have one question.
Yes?
Regarding that tilted basis, means as you are mentioning that orbital angular momentum basis you are measuring, and one of the tilted basis may be that one of the mutually unbiased basis. But in that case, means do you need information that what should be the dimension of the state? And then question comes that for any dimension you cannot have mutually unbiased basis formation. Means the dimensionality needs to be prime number or something. Then how you are solving that?
These are two very good questions. So number one, do I need to know the dimension of the state? No. The dimension of the state is basically, I can choose it because like, okay, of course the dimension is always infinite. Like in a momentum basis, it's infinite. I just choose a subset of modes that are used to construct a second basis. And the tilted basis will then be a superposition of that limited number of modes to make sure that I always work in the same Hilbert space. So usually, of course, if I discretize infinite dimensional systems, I need to make very sure that all the different measurements I do are sampling from the same subspace, because otherwise I could easily fool myself. And it could also be easily tricked by, say, in the QKD scenario. And your second question about the existence of MUBs is also very good, because two mutually unbiased bases exist for any dimension, 3 even, right? So there you don't have to be prime dimensional. But if you want to use d+1 such mutually unbiased bases, then indeed it only works in prime power dimensions, which is why some of the experiments we've just focused to, I mean, since we're discretizing infinite dimensional systems anyway, and we don't really know how to deal with dimension 6, we just skipped dimension 6 and directly went to dimension 7. So here you see, not coincidentally, all the dimensions we actually probed in the table are prime power dimensions, because, yeah, we also wanted to do a full set of MUBs, and we didn't know how to do that in dimension 6, because nobody knows how many mutually unbiased bases actually exist. Or rather, everybody knows it's not going to be 7 in dimension 6, but nobody's able to prove it.
One just quick question, that means how you are fixing that basis in means in SPDC, how you are fixing that it should be 11 dimensional, 7 dimensional, 5 dimensional, 3.
So here, let me use, do you see my mouse actually? Yeah.
Yes, yes.
Okay, wonderful. So here, this was our experiment, or schematics of it. I'm going to explain the rest later. And so what we use is a down conversion source where we want to use orbital angular momentum entanglement. And we use down conversion in a way that the signal and idler photon have opposite polarization, so we can then deterministically separate them on a PBS. And what we actually do is then we use transmission through a spatial light modulator, essentially a little crystal display, to have a phase-only transformation of that is essentially selecting only one of the modes to be then coupling into the single mode fiber. So what it's basically a one outcome projection. It's a bit like a polarization filter, but instead of filtering only H or V or anything in between, we can now display holograms on the spatial light modulator that select only one of the orbital angular momentums to go through and all the other ones to be filtered out. And so we can essentially choose, but just cycling through a couple of them. Funnily enough, our author was really great. So if you see these little symbols here, these are actually projections we made on the SLM. Anyway. Yeah, so we managed to do this experiment, and it was neat because we could show, yeah, with these tilted bases, we can actually do 2 measurements and get really decent results in orbital angular momentum. And then another experimentalist, Rupert Ursin, who then went on to found a really successful quantum communications company, approached us and said, look, I also have high dimensional entanglement in the lab, but I have something very different. I have time bin qubits or qudits. And so what they have kind of a Sagnac configuration. And you can think of it this way, that the photon pair is not, it's basically essentially created in a coherent superposition of times. And this can then be analyzed with a so-called Franzen interferometry scheme. So you kind of have a Mach-Zehnder interferometer where basically the later coming photons interfere with the earlier arriving photons. And these extinction ratios can be used to ascertain coherence in the time bin basis. And since we successfully managed to do high dimensional entanglement, the next question we had, okay, so what about this fabled noise resistance? Can we show it? And how would we even show it? What's a fair comparison? So what we did is we turned on the light in the labs on purpose and tried to make the experimental conditions really horrible, but controllably horrible. And just tried, like, in what discretization dimension can I still find entanglement? And at first it was disappointing because we had some of these old 50, 60 hertz light bulbs. And in the end, with our coincidence windows, we couldn't even destroy the entanglement because the light was essentially flashing really fast. So we actually had to buy special purpose continuously lighting LEDs and focus them directly on our APDs. And then we could get like tunable conditions where we say, okay, let's keep everything the same. Let's just turn up the light in a controllable fashion. And what we saw is, as we turned up the light, we could always compensate for the light being present by increasing the dimension. And in fact, so yeah, I should mention, we also did then the experiment in our OEM lab. Back then, like Robert Fickler joined our lab, who is now leading a quantum photonics group in Tampere in Finland. And Mehul Malik is now a professor at Heriot-Watt and still focuses on high-dimensional entangled systems. Yeah, and we also saw something funny that relates to the question we got earlier, namely, there's now two ways we can actually compensate for the noise. One of them is just more fine-grained resolution of the, essentially choosing a higher dimension. And the other one, as the dimension grows, we can just add mutually unbiased bases, right? For qubits, like if you measure only in X and Z basis, you get a noise resistance of 50%. But if you go to but if you measure in X, Y, and Z basis, you get a noise resistance of 66%. And of course, you can't do more. But as the dimension grows, the real reason you can still basically get that noise resistance is because you can add more and more measurement bases, because more and more mutually unbiased bases exist, provided that you're in prime power dimensions. Yeah, and this led to this plot, which I think I'm gonna discuss maybe the left-hand side. It's the most illuminating. It's the time bin plot where we cycled through dimension 20 to 80. And you see here in orange, that's dimension 10, 20, 40, and 80. And then each of these points, like the first point, the second point in all of these curves corresponds to the LEDs being turned to the exactly same level. So the same level of noise in the lab physically. And here is the threshold. So like this is it's an entanglement witness. And if we're above, it shows entanglement. If we're below, we know nothing. And what you'll see is that as we add more noise, as we add more noise, well, the witness violation goes down and we become separable. But another interesting thing happens. As we increase the dimension, actually our noise increases too. So it becomes a bit of a competition. So as we increase the dimension, we increase the actual noise, but we also increase the noise resistance. And you see, it's not like just a linear advantage. So here, the noise resistance, you see that we could achieve, it goes up, but it kind of flattens. And okay, it has to flatten because it's going to 100%. But we actually did also go to 120 and more, and that didn't work anymore. It's because of how time bins work, for instance. Like, why is there more noise? Like, how can you change the dimension of a time bin? Like, if you discretize certain times, I could either increase the frame to fit more time bins in, but if I do that, I have more time to collect an accidental photon in each frame. So as I increase the frame size, I increase the number of accidentals. But I could also make the time bin smaller. But if I make the time bin smaller, then my clock synchronization is going to give me some limitations, and the jitter will basically mean that I misidentify even correct clicks. So no matter what I do, if I increase the dimension, I increase the noise, but I also increase the noise threshold. But in the end, what we showed is that you can actually win this competition for quite a while. Okay, so I think these are good news concerning the noise resistance. Now, just the last part is, okay, can we now do anything with it? So we've managed to really create a stupidly noisy amount of entanglement in the lab and have these high-dimensional, very noisy states. So can we use them? And it reminded me at once with Marcin Pawlowski, who's a professor in Gdansk now. In 2013, we'd thought about some device-independent QKD, and we're able to prove that high-dimensional entanglement basically manages to close one of the possible loopholes. But at the same time, our labs were not suitable for device-independent QKD, because as you know, it requires loophole-free violation of Bell inequalities. And as a non-experimental group, we couldn't hope to compete. I mean, in the end, a couple of groups did it, but they had quite serious resources. So we thought maybe there's something else we can do if we come to a device-independent QKD. And we actually banded together a bunch of information theorists mostly, and thought about in what way we could devise protocols where high-dimensional entanglement actually gives you a noise advantage. And we realized the big problem with noises, if you look at typical key rates, for instance, in QKD, they'll have two parts. One of them is basically, are you entangled? Because as soon as you're entangled, you have some private randomness. And then there's the error correction part. And the error correction part kills all the advantage because, like, if you're trying to correct an error in a really high-dimensional system, this is going to be extremely expensive. So what we instead do, what we call simultaneous subspace coding. So we're going to use multiple low-dimensional subspaces of a high-dimensionally entangled system simultaneously to basically get the best of both worlds. So we can still prove entanglement that survives because of the high dimensionality, but we're only using low-dimensional subsystems to code in order to get rid of the error correction overhead. And yeah, we were then actually, this was too challenging for us, but we were approached by a group in China, by Xiaomin Hu, Biheng Liu, and basically the group of Guo. And they said, yeah, we have all the necessary ingredients, because they have like 32 SNSPDs already set up on the table and they're ready to do the experiment, something we couldn't afford, and said, okay, great, let's band together. Let's try this. Let's try a new way of creating high-dimensional entanglement in path, and then use this path entanglement directly to show the advantage of our protocol. And this is the result, and it's even better than our theory paper had predicted. I was quite surprised. But there's a simple reason for this. So here you see in red dimension 8, in green dimension 4, and in blue dimension 2. And how far right you go is how much actual physical noise, how much light turned on in the lab you can withstand. And on the y-axis is really just the key rate, really in bits per second of key. And so, non-surprisingly, with no noise, as you increase the dimension, you increase the key. Because, well, each photon carries more than 1 bit, like 3 bits. For an 8-dimensional system and so on and so forth. And of course, here now you see the effect of subspace coding. So like if you have no noise, using 8-dimensional systems without subspaces is the best, because then you get 3 bits per photon. If you use 4-dimensional subspaces, you actually lose out a bit. And if you use 2-dimensional subspaces, you lose out even more. However, once you add noise, you see the effect of subspaces. There's kind of a crossover point where the low-dimensional subspace then outperforms the high-dimensional subspace, because you then get more key per second, despite the fact that the high-dimensional thing works better at low noise.
So just a quick question. So D equal to 8 and D equal to 8 and K equal to 4. That means 8-dimensional subspace and 4 of them?
No, it means 2 4-dimensional subspaces of an 8-dimensional system. So we group the 8-dimensional system into one subspace of dimension 4 and another subspace of dimension 4 separately.
Okay.
Yeah, and that was our experiment with China. And then Rupert left for academia, but we had access to the free space link, so we wanted to upgrade the experiments we had done in a lab. And we got a 10.2 kilometer free space link via a telescope, this Hedy Lamarr telescope on the roof of ICOCI. And we built 2 labs for time-bin entangled qubits, the ones we've seen from the noise resistance, and started to do an actual free space QKD over 10.2 kilometers. And here you see the setup. It's essentially a Sagnac source distributed over the telescope with Fresnel interferometers on both sides, and a classical channel, like with a laser for aligning to find the quantum source, and most importantly, clock synchronization, which we wanted to do in the nanosecond scale. And okay, there's a lot of experimental effort that went into this, but like stabilizing the interferometers, synchronizing the lasers, having the beacons, and so on. But what we really wanted to do is we wanted to measure the key during the day and look at the effect of the dimension. And this is really cute because you can see we started measuring on a summer's night and there was some background light. This is more or less, this is not sunlight or maybe some horizon light, but this is more noise pollution from the city because we're really sending it over an active urban area over like this. These 10 kilometers are really just through Vienna's air. And you see that you get the optimal key rate with 6-dimensional coding, because higher dimensions would introduce extra noise and actually reduce the key rate. And then rain started. So this is the amount of rain. I mean, our meteorological services, they're not like, they only give us a couple of samples. And unfortunately, we just lost the connection during the rain. We didn't find the photons anymore. After the rain subsumed at around 4, you still see some key, optimal dimension 6. And then the sun really comes up. Here is sunrise. And you see that as the sun rises, the optimal coding dimension with the most key actually increases to higher dimensional systems. And with dimension 18, we're able to measure until 6 a.m. This was in summer. We're quite up north, so this was already full daylight. And so we managed, and we could prove that like the qubit encoding did not give us any key anymore. So it's essentially, we managed to, well, initially our hope was to have a 24-hour operation, but the rain and the summer sun directly shining into a telescope just killed the detectors. We now have an idea with better filters to repeat this, but this is basically our free space efforts. And another thing simultaneously we tried is, well, we bought a multimode fiber and tried to transmit high dimensional entanglement through the fiber, and wanted to essentially try to use as many degrees of freedom as possible. So we did it, we used the Sagnac configuration to entangle the system in time and polarization, while at the same time coherently shining on the entry of the multicore fiber, so to have simultaneous time, space, and polarization entanglement that we transmit through a fiber and successfully certify. Yeah, that's already my end. I hope I could somewhat convince you that there is a rich structure of entanglement beyond qubits, and it does have some advantages to think about the physics again when thinking about quantum information processing. We did write a review in my group a little bit on the interaction between theory and experiment of high-dimensional photonics. And yeah, of course, there are some open problems we like to work on now. Okay, the one I always put is entanglement and non-locality. So does every entangled state have the capacity to violate a Bell inequality? Still an open question. Is every entangled state useful for QKD? Similar open question. How much information can I actually put in a photon? Like, given all the degrees of freedom, must be a limit, but like, is it just a technical limit? Is there something fundamental from uncertainty relations? Okay, technical challenge is like, okay, what can we actually measure? Yeah, and so thank you for your attention, and also thanks to all the people that I've mentioned here and many more than them, the collaborators and everybody else who participated.
Okay, thank you, Marcus, for that nice talk and work. So that's okay. So we'll open this up for discussion. Question.
Hi, Marcus. Thank you very much for enlightening talk. Just wanted to ask you in terms of measurement, the higher dimensional state, you're putting it through the SLM and putting it back into a single mode fiber, right?
Yes, so in the OEM experiment.
So the efficiency with which it does that as you go higher and higher, does that lead to the larger noise in higher
Yes.
dimension, or my question is that if we do some other way, will that help?
Yeah, beautiful. That is absolutely correct. That is exactly the problem. The SLM has a finite resolution, and I'm trying to put a phase picture, so I'm trying to put a hologram that cancels out the phase and flattens the phase profile of the incoming transversal mode that I want to measure to be flat. But of course, it has a finite number of pixels. And the more modes I want to distinguish, the more this grainy pixelness will actually lead to misidentifications, because I can't really access this nice continuous space, but I'm really limited by the technical resolution of my SLM.
So there is no fundamental constraint that as you go higher, the noise will increase. I mean, there is nothing fundamental about it. It's a measurement limitation, or do you think something else will pop up if you come up with a new?
I mean, we thought about this, and here there are a couple of things to say. I mean, like, if we keep the beam size the same, as we increase the pixel number to infinity, of course there's no limitation. But the question is, like, what's the smallest mirror I can build? I mean, we're not even talking about Planck length here, because a mirror has to do a couple of certain things. It has to interact with photons in a certain way, or phase retardation. So I'm basically limited by the size of molecules or atoms. I mean, of course, our LCD screens are not there yet, but there seems to be a fundamental limitation in terms of what is the smallest pixel size, and thus what is the smallest resolution, and thus what is the highest number of pixels I can resolve. Another option would be to defocus the beam and with a lens make it really, really large. But once I start doing this, I increase massively the chance of interacting with environment and air molecules or any other distortion. And the slightest distortion would basically mean a massive shift in pixels. So yeah, we didn't come up with a fundamental limitation, but I really think that there's probably going to be one.
Thank you.
Oh, okay. I just have a very quick question, maybe not that quick. So in that subspace that you're using, t equal to 8, so can you give just one example? What is the structure of that subspace that you're using? In terms of, let's say, I guess these are in terms of OM modes, or is it time bin?
This was from this experiment. This is essentially path modes. So here, here the idea was the following. So we have a crystal, and we use a beam displacer. Sorry, it is maybe not that. I'm drawing with the mouse now. So like we have a blue pump laser at 405, and we essentially use beam displacers to pump the crystal coherently in many places. Okay, this is now the ugliest drawing I could think of, but you get the idea. So like if this is our BBO or PPKTP, we're basically using a coherent superposition of different pump positions to then create path entanglement. This is this setup here. I mean, I know it's hardly recognizable. The advantage of this is, of course, that we can pump stronger, because one of the to get more photon pairs, because we don't have such a problem with multi-photon emission and damage threshold of the crystal, because we can basically, these are separated, I think, 2 millimeters apart, they pump.
So these 4 lines are essentially your 4 sets of subspaces, right?
Exactly, that would be the setup, so to speak, for 4-dimensional entanglement, to pump the crystal in 4 different places and then lead each of the resulting photon pair creations along different paths, and then have an extra detector for each path. This is why I mentioned the 32 SPDCs, because essentially SNSPDs, because each path then needed its own detector.
So this is then like hyper entanglement, right? I mean, you are utilizing path, I mean, time bin, as well as the spatial aspect of
yeah. So I mean, indeed, I would say, so for instance here, this was pure time bin or pure pure OEM. This experiment was actually pure path, so we ignored time bin and polarization. this is why I also quickly showed this multicore fiber experiment, because this is really one where we do all, like, this is really hyper entanglement.
Okay. So I mean, just a very quick follow-up then. So suppose I want to do this using OAM mode, right?
Mm-hmm.
So I mean, is there any way of choosing those 4 subspaces using just the OAM mode? For example, ±1, ±2, ±3, ±4. Is that something?
Yes, in principle, of course, you could choose any subspace, but there is a better and there is a worse choice. And that depends on the orthogonality of the modes. So within each subspace, you want to decrease the chance for error. And this you can do by basically choosing the most orthogonal modes. I mean, I know in truth, of course, all orbital angular momentums, all Laguerre-Gauss modes are orthogonal. But actually, when you look at it with the SLM and the coupling to the single mode fiber and you do the measurements, which we did, you realize it's not 100% orthogonal. So if I create a 0 mode and set the SLM to detecting the 1 mode, there's still a chance that I get a detection event. So they're not perfectly orthogonal, simply because our measurements aren't perfect. So what you would want is, and then you characterize the overlap, the scalar product of all potential modes that you actually have from the measurement setup, and then you choose the subspaces such that the orthogonality kind of is maximized for each subspaces separately.
Nice. So, but then the point is that if I choose 8 OAM modes versus 4 subspaces of 2 dimensions each, from noise sensitivity perspective, the other one would be better.
Sorry, the microphone wasn't loud enough. I didn't.
Okay. Now I'm saying the what I see that like in OM basis or the time
Mhm.
if I have an 8-dimensional mode versus 4 subspaces each of 2 dimensions, from noise sensitivity perspective, the other one would be better, right?
Yeah, exactly. The noise resistance. I mean, this is shown here. I mean, like the optimal dimension and the optimal subspace dimension really depends on the amount of noise I'm experiencing. This is also why this is what we wanted to see here, right? You see that as the environmental conditions change, the optimal dimension changes too.
Okay. Yeah, this might be interesting exploring with the OM mode. That would be interesting.
Yes, absolutely. We didn't do this. So this we only did with time bin so far.
So again, one question from. Okay, so I'll let others go. Sorry.
I have just one question regarding this experiment. You are changing the strength of the noise. Means I saw that there is an lamp is there to introduce some noise, where you are showing the violation of entanglement. Yes, yes, ambient line. So how you are quantifying that some noise amount is 0.4, 0.3?
So, okay, here there was, of course, sunlight that was beyond our control, and we just recorded the sunlight through singles in our detectors. Here we quantified the extra coincidences that result from turning on the lamps per second. So we basically did the experiment without the source, turned on the lamp, and then just recorded the number of coincidences per second that came as a result from the lamp, and used these as standardized settings for the experiment.
Okay. Okay, so maybe one last question. So in that, you send that high dimensional entangled photon through the fiber, multimode fiber, right?
Mm-hmm.
So the entanglement survives when it goes to the fiber, or are you using some special kind of fiber for that?
Well, this is a box standard multi-core fiber. This is now telecom wavelength. So here we pump with 780 nanometers, and all the entanglement survives separately. So like we can certify polarization entanglement, time bin entanglement, and path entanglement. Although the path entanglement is of course the most challenging, because I don't know why, but like the fiber is 411 meters, and like some of the cores are longer than others, effectively. I don't know why. So we had to look for a very long time to use some piezo stages that you see here to actually try and see to get coherence between the different paths. And this also changes over time. So the slightest change in temperature or moving the fiber around immediately made us lose the path entanglement because, yeah, to get them all in phase is a bit of a challenge. I think if you have a fixed fiber lying somewhere and you have all these piezo stages, you can automate the process, but the experiment was a bit of a challenge.
So, but I mean, do you have any, hint as to if we send the OM mode through the fiber, will the entangle still survive, or do you think?
I do not. I never did that. But of course, a multi-core fiber is not suitable because these are all, each core is single mode. However, there are, of course, multi-mode fibers. And I know both Mehul Malik, my former postdoc, who is now professor at Harvard, he has successfully transferred OEM entanglement through a multi-mode fiber. And I think also Davide Bacco and I think some more people.
I see. Okay. Okay. Maybe I'll talk to
Mehul.
Okay.
I've not tried that myself.
Okay. Then if Mehul, I'll talk to Mehul. That will be interesting. If the multi-dimensional OM entanglement that can survive through fiber, that will be quite interesting. Last, so you showed through your technique that you can verify entanglement just being measurement in two bases. Is there any way that you have or thinking of kind of quantifying high dimensional entanglement, or is just at this point it's just verify?
No, in fact, so with the two bases already back then, what we actually verify is the fidelity with a target state that we can choose. And from the fidelity, we can compute lower bounds on the Schmidt number, i.e. the entangled dimension. So we can quantify the dimensions. And there are some more papers I didn't mention that you can actually quantify things like entanglement of formation or concurrence from the same outcomes. And there's a bit of a trade-off. There's no free lunch. Like the more bases you use, the better the bounds become. So in the noisy case, so like if you have pure states or close to pure states, then with two measurements, you can already certify maximal entanglement of formation or maximal Schmidt number. But as the noise increases, you need to add more and more bases to actually get a reasonable lower bound on quantifying entanglement.
Okay. So this is still the like quantifying the lower bound, but not the entanglement itself. Just like we do in the case of 2-qubit state in terms of concurrence. That is at this point not possible for this continuous variable or high dimensional.
Right? I would firmly believe that this is possible. Never possible. Wait, I don't know. I had some backup slide, but no. So the reason why I think it's not possible is for qubits, we know like if you have a full state tomography, we can quantify entanglement through concurrence and we can compute it analytically. But we know already for 2 qubits, 3x3 systems, it is still an unsolved problem. Even if you have all the measurements, like a full density matrix without error bars, there's no method that guarantees you to converge that tells you whether you're entangled or not. Okay. So it's a so-called NP hard problem. So we believe there will not be an efficient algorithm to ever exist that will answer this question in a reasonable amount of time. So in this complexity theory, guys, I mean, I guess in some sense we're doomed in higher dimensions to only ever have lower bounds. We can certify we're sure that there's a certain amount of entanglement, but there could always be more. And it might be algorithmically unreasonably taxing to find out more. While at the same time, what is hidden might be very small because like the strong entanglement, the free entanglement and all that can be easily detected. And most of the things that remain obscure is this little bit of extra bound entanglement. And maybe for practical purposes, we don't even need to care about that so much. Although I find it very interesting.
Okay. This is really the final question. So other than QKD, what do you think are the possible or potential uses of high dimensional entanglement?
That is a very good question. I don't actually know a lot of uses. I mean, like there's of course oblivious transfer and non-malleable encryption as like two primitives that could benefit from it. Then just maximizing the channel capacity, not for a secret key, but just using a channel to its absolute maximum capacity basically means this is where high dimensional coding also comes in classical systems, right? I mean, there are classical OEM protocols and things because you just want to use, so to speak, the full bandwidth of your signal to transfer as much information as possible. But yeah, genuine quantum protocols, I mean, there's dense coding, oblivious transfer, QKD, but I mean, like the real question is what does quantum bring to the table that classical cannot do? And you can certify entanglement, and with this you can certify a sort of monogamy, a pureness. It's really just the two of you that share the state. So I feel like the only application I can really think of is in cryptography, like that is genuinely quantum.
Okay. Well, let's thank Marcus one more time.
Yeah, thanks a lot for listening.
Thank you so much. Okay.